Welcome to the debate.
Our focus today is on causal latency theory, or CLT. Well, a very ambitious new framework that claims to unify quantum mechanics and gravity. And it does this by defining the universe not by fields or particles, but as a relational network constrained by a finite information bandwidth.
Exactly. And the theory makes two profoundly radical claims. First, that fundamental particle properties actually emerge from topological structures. And second, that this information theoretic basis resolves some really long-standing conflicts, like the particle mass hierarchy problem and, of course, quantum non-locality.
So the central question we're tackling today is really this. Does CLT successfully deliver a truly rigorous, unified kinematic framework, one whose models accurately reflect fundamental physics? Or do its remarkable predictive successes rely on mathematically complex, high-dimensional topological terms that in the end lack a fundamental physical derivation?
And I'll be arguing that CLT provides a robust new physics of process, and that it's validated by its incredibly predictive topological models, establishing a necessary computational foundation for reality.
And I'm going to challenge the foundational basis of the theory. I'll be questioning whether the complexity that's required to match the observed data really compromises the theory's initial elegance, particularly when you look at its reliance on nonlinear scaling laws and the practical impossibility of its most critical definitive tests.
Well, CLT starts from a place of just breathtaking rigor and simplicity. The foundational move is purely kinematic. It's about recognizing that because information travels at a finite speed, the universe must operate with a finite refresh rate. And that means there's an inherent temporal delay or latency in all causal interactions. This simple premise, this one idea, leads directly to the mathematical derivation of the Heisenberg uncertainty principle.
And I'll grant you, that part is elegant. It is. It transforms quantum uncertainty from, some philosophical mystery about observation into an inherent computational limit of the universe itself. It's a kinematic constraint, not just an observational fuzziness. And crucially, the theory moves beyond simple kinematics by showing that the properties of fundamental particles, their charge, their spin, their mass, they all emerge from topologically stable structures, which the theory calls causal knots. These are stable regions of what you could call information flow turbulence. The empirical success here is just overwhelming. The theory achieves astonishing numerical accuracy in deriving the mass hierarchy of the heavy leptons, specifically the muon and the tau, by correlating their properties with specific geometric winding numbers and the vacuum's derived resistance to that complexity. And on top of that, it resolves quantum non-locality, the classic EPR paradox, with a concept called boundary locality.
This isn't a violation of relativity, it's a structural integrity. Entangled particles share memory coordinates on the boundary of the causal manifold, providing a geometric shortcut, like shared information addresses that circumvent the need for any faster-than-light communication in the bulk.
Okay, I see why you find those numerical results so compelling. And I admit, the 99% accuracy achieved in matching the heavy lepton mass ratios is, it's an incredibly powerful result. But I would frame the argument differently. While the initial kinematic premise, that latency drives uncertainty, is elegant, the intellectual step from that simplicity to the necessity of these complex, nonlinear scaling laws that you need to generate mass it's substantial, and it requires far more physical grounding than is currently provided. For instance, to get that near-perfect prediction for the tau mass, the model relies on a derived factor known as the causal impedance feedback scaling term. Now, this term is proportional to the winding number, which describes the knot's complexity, raised to the exponent 4.5. That reliance on an extreme nonlinear, high-exponent phenomenology, it raises significant questions about the physical source of that geometric scaling law, where, fundamentally, does that 4.5 exponent even come from? If the physics is truly primary, the metric equation should yield this scaling naturally. Instead, it feels like it's derived recursively from volumetric simulations. It's the exponent required to make the math match the observation, rather than a prediction from the foundational theory. And furthermore, When CLT tries to tackle real-world complex systems, say, explaining macroscopic quantum coherence in biology, it has to invoke hyperholography. This posits that complex systems access nested topological dimensions, n greater than or equal to 4, within the causal manifold. And that immediately strains the initial simplicity of the model by requiring us to accept a high-dimensional computational subspace. It's a profound conceptual cost just to maintain biological stability.
But the geometric foundation for mass is absolutely sound, and that nonlinear exponent is a mathematically required consequence of dynamic vacuum resistance. It is not a fitted parameter. It's crucial to understand the mechanism here.
Okay.
We derive the muon mass by modeling it as a specific topological structure, a trefoil knot, which introduces geometric torsion into the information flow. This torsion dramatically increases its causal tension compared to the fundamental unknotted electron. So the mass difference, you see, it's not random. It's a topological phase transition. The nonlinear feedback, the S proportional to kappa to the 4.5, is a necessary consequence of what we call vacuum stiffening. As the topological complexity, defined by that winding number kappa, increases, the local refractive index of the vacuum, its effective latency, has to scale nonlinearly to contain the increased phase gradients. This stiffening is the vacuum physically resisting the containment of higher topological density. It unifies mass generation with the dynamics of the vacuum itself. It explains why inertia exists. It's the resistance of the computational fabric to localized complex information density. And that scaling law emerges directly because the inertial mass density is proportional to the causal tension, which is dominated by the square of the gradient of the phase fields.
I admit the idea of vacuum stiffening related to complex information gradients is it's an elegant solution, but I do have to push back on the claim that the exponent is necessary and not just fitted. You're saying the 4.5 power law is required, but how is that specific value derived independently from the known mass ratio? Is the vacuum action functional minimized and the resulting equation just naturally yields 4.5? Or is it that the 4.5 exponent, when you plug it back into the model along with specific geometric aspect ratios, like the 0.21 ratio required for the tau, is what allows you to achieve that 1% accuracy?
Right.
If the mechanism is truly fundamental, this deep link between mass and geometric torsion, then the entire relationship, including the precise geometric constraints, should emerge directly and uniquely from minimizing the vacuum action functional. It shouldn't require external constraints or, recursive optimization against empirical data. It seems the model requires us to presuppose the existence of a specific causal knot topology for every particle generation, rather than predicting the necessity of that precise structure from the first principles of causal geometry.
I see the point, but the specific aspect ratio is a constraint on the solution set, not an arbitrary fit. That ratio defines the stability boundary of the higher-order topological solutions allowed within the causal envelope. It's analogous to boundary conditions in classical field theory. It's the limit imposed by the local speed of light. But the core of the debate here has to shift, I think. If the foundations are complex, that brings us inevitably to the testability of the theory itself.
Okay, so let's talk about that. A robust scientific theory has to be practically falsifiable. And while CLT proposes some crucial tests that offer deterministic deviations from standard physics, which is a major strength, many of these tests require technologically, impossible thresholds.
For now.
For now, consider the centrifuge Bell test, proposed to test the concept of Rindler decoherence. The idea is brilliant, I'll give you that. If quantum entanglement is fundamentally dependent on the causal horizon structure, then subjecting entangled particles to extreme acceleration should cause the entanglement to dissolve. The horizon literally slices through the correlation length. The problem? The acceleration required is so extreme that the necessary Rindler horizon distance approaches the size of the particle correlation length. Simulations show this acceleration is far beyond current mechanical limits. Even with sophisticated ion traps, you are essentially asking us to accelerate a lab frame to the point where the local spacetime metric is approaching that of a micro black hole. frequency to induce exponential pair creation at just 1% of the classic Schwinger limit. While it would theoretically prove the vacuum's refractive properties, achieving the required energy density and that precise resonant tuning is simply far beyond any current industrial or laser capability. If the theory can only be falsified by impossible tests, what credibility does it really have in the near term?
Well, I'm not convinced that focusing solely on the upper bounds of technological feasibility is a fair critique. The theory offers specific, high-leverage tests that are not impossible and, in fact, are within the precision envelope of existing infrastructure. The fact that the theory requires technology at the limits of possibility just reflects the profound depth of the claims being made. We are probing the computational limits of reality itself. So let's look at the near-term tests. The Rindler decoherence curve, which you mentioned, it provides a unique, sharp drop-off target for next-generation zettawatt lasers probing the Schwinger regime. We are building those lasers now. So this is the most direct microscopic test of the horizon hypothesis, providing a precise, unique, and non-standard model prediction for entanglement breakdown under extreme energy density. But more immediately, consider the LIGO anisotropy test. This is entirely within current capability. We predict that the noise reduction achieved by LIGO's squeezed light states, a quantum optical technique they use to reduce vacuum noise, should be subtly modulated by the detector's orientation relative to what we call the causal headwind.
Which is the motion relative to the CMB dipole.
Exactly. The causal headwind is just the Earth's motion relative to the universe's zero-point reference frame, which is approximated by the cosmic microwave background dipole. If the universe's fabric has a finite latency, the Earth moving through it creates a causal wake. We predict this relative motion should induce a subtle modulation on the order of 10 to the minus 6 in the detector's quantum performance over sidereal timescales. This signature is deterministic. It's measurable within LIGO's current precision budgets, and crucially, it is a direct, measurable violation of the strong equivalence principle. The result is testable today and provides a smoking gun for the entire concept of finite information latency and the vacuum's refractive properties.
That is an extremely precise and compelling counterargument. The LIGO test is certainly the most promising near-term avenue. But let's return for a moment to the necessary complexity of the theory. To reconcile CLT with the real world, you require this concept of hyperholography. We're asked to accept that biological complexity, like a folded protein or even the human brain, achieves its stability by accessing dozens of extra dimensions. I mean, that is a massive conceptual leap.
But the high-dimensional topology is justified precisely by the stability and coherence we observe in high-entropy natural systems. The hyperholographic extension resolves paradoxes like the protein folding problem or the Levinthal paradox, which notes that proteins should take astronomical amounts of time to fold by random search, yet they do it almost instantly. CLT shows that complex systems maintain their integrity against rapid thermal decoherence by accessing higher topological dimensions, potentially up to, say, d-topo of about 40. Imagine the universe as a vast computational machine. A high-dimensional state acts as a causal shield. Why? Because in high dimensions, the probability of a random thermal hit, a noise packet, aligning perfectly with the system's high-dimensional state vector, just drops exponentially. The high-dimensional geometry statistically dilutes the noise.
This explains why biological coherence is maintained so robustly at 310 Kelvin, a temperature that, based on standard quantum mechanics, should immediately destroy any delicate quantum coherence. Topology acts to reduce thermodynamic friction, protecting the informational state of the system. The complexity is justified because it solves a deep, deep problem in natural history.
The decoherence problem and the Levinthal paradox. It implies that complexity itself is defined by the capacity to access these nested dimensions in the causal manifold, which it shifts the foundation of biology from chemistry to informational geometry. However, I would frame the stability issue differently. Even if the high-dimensional state is protected from informational noise, random thermal fluctuations, CLT itself notes a critical caveat. The entire high-D system is still metric anchored to the 3D bulk. The actual hardware, the atoms, the covalent bonds, the physical neurons, exists only in D equals 3.
Sure.
This means the stability is merely shifted, not eliminated. if you subject the system to structural noise, for example, mechanically stressing or pulling apart a protein, forcing its 3D components onto a non-geodesic path, the informational structure in the higher dimensions is still vulnerable to collapse, revealing what the theory terms a topological force hysteresis. The fragility is not cured by adding dimensions. It's simply shifted from vulnerability to informational entropy to vulnerability to structural mechanical disruption. This suggests the proposed causal shield is robust against temperature, but fragile against manipulation.
But that structural vulnerability speaks precisely to the necessity of the dimensionality. The theory isn't claiming immunity, it's defining the constraints of existence. The Heidi architecture explains the coherence and stability required for life to persist against probabilistic thermal decay. The metric anchoring explains why the system remains physically addressable and subject to macroscopic mechanical forces. So the system is designed not for absolute immunity, but for optimal computational efficiency and robustness within the known thermodynamic constraints. If the theory is right that complexity is fundamentally defined by access to higher topological memory, then we have the ability to begin designing systems, biological or artificial, that optimize these geometric constraints. That's metric engineering. That's moving from merely understanding the laws of physics to designing the very fabric of physical reality itself.
So we've established that causal latency theory provides a mathematically unified framework. It derives constants like particle mass from topological necessity and offers a kinematic explanation for both quantum uncertainty and gravity. The theory's approach, from explaining leptons to predicting planetary-scale causal wakes, suggests that the universe's structure is emergent from information flow and its limitations. The predictions, however experimentally demanding, are sharp, quantifiable, and they specifically differentiate CLT from the standard model, offering the possibility of metric engineering based on the vacuum's refractive properties.
I think I would come at it from a different way. While CLT shows profound predictive power, especially in matching the heavy lepton-mass ratio, the intellectual step required to accept its foundations is immense. The reliance on these extremely nonlinear power laws for mass generation and the conceptual invocation of high-dimensional topological fibers, they require far greater physical derivation from first principles. And moreover, the most critical definitive test of the theory, whether it's the high-sensitivity LIGO anisotropy test or the technologically limiting Schwinger breakdown prediction, demonstrate the incredibly high threshold required to rigorously confirm these profound claims about the universe's computational fabric.
Understanding the universe's fundamental structure requires evaluating reality not just in terms of energy and mass, but in terms of information and its fundamental latency. And I think this single realization forces us to confront whether the elegant simplicity of that initial latency premise justifies the enormous conceptual and mathematical complexity required to describe the world we actually observe.